The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so we are going to continue looking at what happens when we have non-independent variables. So
I have a delivery here for Jason Yu.
I'm afraid we don't take deliveries during class time, sorry.
Oh, well, here, I'll just leave it here.
Okay, please take a seat. Thanks. Oh. No, thanks. Okay. Okay, so Jason Yu, please claim your package at the end of lecture. Okay, so last time we saw how to use Lagrange multipliers to find the minimum or maximum of a function of several variables when the variables are not independent. And today we are going to try to figure out more about relations between variables and how to handle functions that depend on several variables when they're related. So just to give you an example, in physics very often you have functions that depend on pressure, volume, and temperature, where pressure, volume, and temperature are actually not independent, but they're related, say, by PV equals nRT. So, of course, then you can substitute and express the function in terms of two of them only, but very often it's convenient to keep all three. But then we have to figure out what are the rates of change of P and V with respect to T, with respect to each other, the rate of change of F with respect to these variables, and so on. So we have to figure out what we mean by partial derivatives again. So, okay, I mean, more generally, let's say just for the sake of notation, I'm going to think of a function of three variables, x, y, z, where the variables are related by some equation that I will put in the form g of x, y, z equals some constant. Okay, so that's the same kind of setup as we had last time, except now we are not just looking for minima and maxima, we are trying to understand partial derivatives. So the first observation is that, if x, y, and z are related, then that means, in principle, we could solve for one of them and express it as a function of the two others. So, in particular, can we understand, even without solving, maybe we cannot solve, can we understand how the variables are related to each other? So, if, for example, z, you can think of z as a function of x and y. So, we can ask ourselves, what are the rates of change of z with respect to x keeping y constant, or with respect to y keeping x constant? And of course, if we can solve, then we know a formula for this, and then we can compute these guys. But what if we can't solve? So how do we find these things without solving? Well, so let's do an example. Let's say that my relation is x squared plus yz plus z cubed equals 8. And let's say that I'm looking near the point xyz equals 2, 3, 1. So let me check. 2 squared plus 3 times 1 plus 1 cubed is indeed 8. Okay, but now if I change x and y a little bit, how does z change? Well, of course, I could solve for z in here. It's a cubic equation. There is actually a formula, but that formula is quite complicated. We actually don't want to do that. There's an easier way. So how can we do it? Well, let's look at the differential of this constraint quantity. Okay, so if we call this G, let's look at dG. So, well, what's the differential of this? So differential of x squared is 2x dx plus, I think there's a z dy, there's a y dz, and there's also a 3z squared dz. Okay, you can get this either by implicit differentiation and the product rule, or you can get this just by putting here, here, and here the partial derivatives of this with respect to x, y, and z. Okay? Any questions about how I got this? No? Okay. So now what do I do with this? Well, this represents somehow variations of G. But, well, I've set this thing equal to 8. And 8 is a constant. So it doesn't change. So, in fact, well, we can set this to 0. Okay? Because, well, if I call this G, then G equals 8 is constant. That means we set dG equal to 0. Okay. So now let's just plug in some values at this point. That tells us, well, so if x equals 2, that's 4 dx, plus z is 1, so dy, plus y plus 3z squared should be 6 dz equals 0. And now this equation here tells us about a relation between the changes in x, y, and z near that point. It tells us how if you change x and y, well, how z will change. Or it tells you actually anything you might want to know about the relations between these variables. So, for example, you can, move dz to that side and then express dz in terms of dx and dy. Or you can move dy to that side and express dy in terms of dx and dz, and so on. It tells you at the level of the derivatives how each of the variables depends on the two others. Okay, so just to clarify this, if we want to view z as a function of x and y, then what we will do is we'll just move the dz's to the other side, and it will tell us dz equals minus 1 over 6 times 4 dx plus dy. And so that should tell you that partial z over partial x is minus 4 over 6, well, that's minus 2/3. And partial z over partial y is going to be minus 1/6.